In the second half of this lecture, let's turn our attention to the internal shear force and bending moment in the beam, and to see how they can be calculated when a distributed load is present. As I mentioned before, here we should not replace the distributed load with a concentrated load, but why not? I'm going to answer this question using an example. Consider a simply supported beam subjected to a uniformly distributed load of W. Let's obtain shear and moment in the beam when it's subjected to the distributed load and when it's subjected to the equivalent concentrated load. First, we need to calculate the support reactions. For this, I'm going to replace the distributed load with its equivalent concentrated load. Then I'm going to write the equilibrium equations and solve them for the unknown reactions. So I have WL over 2 for the left and the right vertical reactions. Now let's determine shear and moment equations in the beam for each load case. For the distributed load, we have For the equivalent concentrated load, we have By the way, if you're not sure how these equations are obtained, please see Lecture 7. Note that the two sets of equations are not the same. The difference becomes even more obvious if we graph the equations. Here is the shear diagram for the left beam, and here is the shear diagram for the right beam. Clearly, the two diagrams are not identical. Observe that shear in the right beam is generally larger than shear in the left beam. For example, at point C, the left diagram gives a shear value of WL over 4. However, the right diagram gives a shear value WL over 2 for point C. This means that when we replace the distributed load with its equivalent concentrated load, we overestimate shear value in the beam. Similarly, for bending moment, we have this diagram for the left beam and this one for the right beam. Again, this shows that bending moment under the distributed load is less than bending moment under the equivalent concentrated load. Therefore, to obtain accurate values for shear and moment, we should perform the calculations using the distributed load, not the equivalent concentrated load. Now let's look at a few examples for calculating shear and moment in beams subjected to distributed loads. Example 5. Here we're given a beam subjected to a triangular load. We wish to determine the shear and moment equations for the beam. From example 2, we know that this beam has a vertical reaction of 4 kilonewtons at A and a vertical reaction of 8 kilonewtons at B. To write shear and moment equations, we need to cut the beam at an arbitrary distance x from the left end of the beam. We can now formulate the shear and moment equations by writing the equilibrium equations for the left segment. In order to do that, however, we need to know the intensity of the load at the cut point. Let's refer to it as h. We can use the geometric properties of similar triangles to find h. We can write h over x equals 2 over 12, or h equals x over 6. The free body diagram for the left segment of the beam then can be drawn like this. Summing the forces in the y direction, we get Vx equals 4 minus x over 6 times x over 2. Note that here x over 6 times x over 2 is the area of the triangular load applied to the left segment. Similarly, bending moment equation can be written as mx equals 4 times x minus x over 6 times x over 2 times x over 3. Here also x over 6 times x over 2 represent the area of the load triangle, and x over 3 is the distance from the centre of the triangle to the cut point. The area times this distance gives the moment of the distributed load about the cut point. In summary, the shear and moment equations for the beam are Example 6. In this example, we consider a beam subjected to a trapezoidal load. As was discussed in example 3, this beam has a vertical reaction of 10 kilonewtons at point A and a vertical reaction of 14 kilonewtons at point B. Similar to the previous example, in order to find the shear and moment equations for the beam, we're going to cut the beam at an arbitrary distance, x, from the left end of the beam. For simplicity, let's divide the trapezoidal load into a rectangular one and a triangular one. Note that the height of the triangular segment at x can be determined using similar triangles, that is, h over x equals 2 over 12, or h equals x over 6. So now we can draw the free body diagram of the left segment like this. The shear force can then be written as Vx equals 10 minus 1 times x plus x over 6 times x over 2. Mx equals 10x minus 1 times x over 2 minus x over 6 times x over 2 times x over 3. In summary, we have